So we have now found some specific solutions to our partial differential equation. And while doing so, we encountered this equation here where we determine specific values of lambdas as eigenvalues. And actually, if we look a bit closer, the equation that we see here actually looks a little bit like the eigenvalue equation as we know from operators in Hilbert spaces. So if I identify the function phi with some state vector phi, and I consider this derivative here as an operator acting on that function, what we have here actually is one-to-one an eigenvalue equation of an operator acting in a Hilbert space. And indeed, one can make a connection between these functions that are the solutions to our differential equations and the Hilbert spaces. And to this end, we will now introduce the Hilbert space H of functions phi of x that obey these boundary conditions here. So these were the boundary conditions that we wanted to fulfill for our eigenvalue equation. It is actually easy to see that the functions phi of x form a vector space, because if I have two functions phi1 and phi2, which both fulfill these boundary conditions that at 0 and L they're equal to 0, then it's easy to see that also any linear superposition of them fulfills these boundary conditions, and then by definition also lies in this vector space. So indeed, we can also define a vector space with functions. Now, what more do we need to form a Hilbert space? Well, essentially what we need to be able to do is to have a product of a bra and a ket vector, or in other words, we need to define a scalar product. So we need to define a scalar product for two of these functions of this Hilbert space. And the correct way of doing that is to introduce the scalar product as an integral from 0 to L of f of x star times g of x dx. Now, it's also easy to check that this is a proper scalar product, whether it's linear and these kind of aspects. So I encourage you to check this yourself with pen and paper. So what we see here is that basically the function g here forms essentially the ket vector, whereas the function f star basically forms the bra vector. So in some sense, you could say the complex conjugation here is like getting from a ket to a bra vector. Now, when we dealt with operators, then we were especially interested whether they were Hermitian, or when we talk about differential operators, one also talks about self-adjoint. So it's the same, just different names for the same thing. And in particular, in our case, you would be interested whether this operator that we have here is Hermitian. And how do you check that? Well, the definition of it being Hermitian is whether the matrix element FLG equals to the matrix element F Hermitian conjugate of L and G for all possible F and G that we have in the Hilbert space. Now, how do we actually define the adjoint here? For that, I refer you back to how we defined the adjoint formally in the Hilbert space lecture. So if we have some state which is phi, which is generated by acting with L and G, then if I take the bra vector, then this corresponds to the Hermitian adjoint acting on the bra vector G. And what in particular, what this means for us is that, normally this operator, when it acts on a ket vector, it means it would act on this function here in the scalar product. And if we have the adjoint operator, so the Hermitian conjugate, which is here, it would act on the first function that we have here in the scalar product. So let us just write this down explicitly. So the matrix element FLG, that is given by our scalar product where we act with the derivative operator on G, and the matrix element of the Hermitian conjugate is given by acting with the differential operator on F. So this is how we have the Hermitian conjugation implemented here. Now, what we would like to see is whether these two expressions are the same. And, at first glance, they're not. Once I have here an operator acting on G, and here I have the derivative acting on F. So we need to try to prove, to show that these are actually the same. We need to try to bring these derivatives to the other side to act on G. And this we can do by applying the formula for partial integration. So let's write this here in a little bit more compact way. So this is the same as minus h squared over 2m. So we can just take that out, it's just a constant, times integral from 0 to L f star second derivative of x times g of x. So taking derivative and taking the complex conjugation, those things commute, so we can also bring that inside. And for this we can actually now use the partial integration formula, because just to remind you, if we have an integral of the form integral from a to b first derivative of u times v dx, then this is actually the same as u and v taken at the boundaries a, b, minus integral from a to b u, and then the first derivative of v dx. So we basically really transfer the derivative from one function to the other. And this is what we also want to do here. So if we do the first, we get that this is equal to plus h squared over 2m integral from 0 to L f star prime x g prime x dx. So this is this integral part. So there's a minus sign here. That's why we get a plus here. And well, we transferred one d dx from here to the function g. So that's why we have f star prime and g prime here. And then we also need to look at these boundary terms here, and those are given by minus h bar squared over 2m, and then the functions f star prime of x, g of x, taken at the boundaries 0 and L. And what you see here is that because of the boundary conditions, that g of 0 equals g of L equals 0, this term cancels. So we're left only with the integral term. Yeah, and now you immediately see how this goes further. Apply the partial integration once more. Then I get minus h bar squared over 2m integral from 0 to L f star of x g double prime x dx plus h bar squared over 2m, and then the boundary terms of f star of x g prime of x from 0 to L. And here, again, we can use now the fact that f of 0 equals f of L equals to 0, to also make use of the fact that this boundary term is vanishing. So it's important that in both cases we had actually the bare function without any derivative in there, so g and here f, because this boundary condition holds for the function. The derivative doesn't have to be 0 at the edge, of course. That is the difference. But now if we look closely at this term that we get here, we immediately see that this one here is the same as f L g. So this means that indeed this operator L here is self-adjoint. Okay, what does it mean for an operator to be Hermitian or self-adjoint? Well, what we know is that for an Hermitian or self-adjoint operator, the eigenfunctions form an orthonormal basis. So the solutions that we found before, the eigenvalues, they also had corresponding eigenfunctions. These were the sine kx functions. So these are actually the eigenfunctions, and they form an orthonormal basis. And in fact, this means we can expand any function with the correct boundary conditions using this orthonormal basis. Just to remind you, I wrote down again how in a Hilbert space, if you have an orthonormal basis un, how you can expand any state vector. And this is that the state vector phi is given by a sum over all the orthonormal basis vectors times a coefficient which is given by the scalar product of the orthonormal basis vector un with the state vector phi itself. Now in our case, these orthonormal basis vector corresponds to the sine kx terms. So I wrote it out here. It's a sine n pi x over L. Now, just a little subtlety, which we didn't pay attention before. Here I say orthonormal basis. So I also need to normalize these sine functions with respect to the scalar product that we defined. And this gives rise to this square root over 2L normalization factor that I wrote down here. Now, with that, we can then directly go ahead and use that to expand the initial conditions of our problem. Because what we need to solve, we wanted to solve it for a particular value of the boundary conditions, so the phi of 0 and phi of L equals to 0. Now this we already did. What we didn't take into account yet is the initial condition, and the initial condition was that for t equals to 0, psi should be equal to psi 0 of x. Now, we were able to find the special solutions, and if we can now express these initial conditions in these special solutions, then we also have a complete solution for this general initial condition. And what we now basically do is we apply the formula for expanding a state vector in an orthonormal basis. We can express psi 0 of x as sum over n equals to 1 to infinity, a coefficient times square root of 2 over L times sine n pi x over L, where the latter here is our orthonormal basis. And this coefficient Cn here, that is given by this matrix element of the orthonormal basis vector with the state vector itself. So the Cn are now given, in our case, the scalar product is defined with the integral as an integral from 0 to L times square root of 2 over L times sine n pi x over L times psi 0 of x dx. Now, I don't write a star here. Well, that's because the sign is just real. So for this, in this particular case, it doesn't matter. I actually only wrote the star there so that you know that for a general case of complex functions, you would actually need the complex conjugate in the definition of the scalar product. Now, but with that, we can then immediately write down the complete solution because we know how each of the orthonormal basis vectors, how that behaves in time. It had the simple time dependence of e to the minus I lambda n t over h bar, so that our complete solution becomes psi of t x equals to sum over n equals to 1 to infinity Cn, so these are the Cn's that are defined here, times e to the minus I lambda n t divided by h bar times square root of 2 over L times sine n pi x divided by L. And that is now our final solution, our final and general solution to the partial differential equation with the given initial and boundary conditions. Now, if you look into a true math book, you will see that we skipped over a couple of subtleties. So there are actually some subtleties about defining the self-adjoint operators of the kind that we have. They're so-called unbound operators, and then things are a little bit more tricky. But, as I said, this is a course given by physicists. So, we can actually rely on somebody else having figured out these fine details for us. And what we just did here simply works. Now, how does that carry over to other partial differential equations? So I just showed it to you for a specific differential equation. And indeed, one can try to use this recipe also for other partial differential equations. So the first step would always be try to do a separation ansatz. And once that works and you get two independent ordinary differential equations, identify which of them you should use as the eigenvalue equation. That really depends on what are the boundary or initial conditions. So in our case, it was quite natural that we had to use the equation for phi as our eigenvalue equation. Then we have to solve this eigenvalue equation and insert the eigenvalues into the other equation and solve also that one. And then you have all the special functions. And then basically you have to see whether your operator that you had was actually Hermitian, so that we have an orthonormal basis. And if that's the case, then you can use the orthonormal basis to write a general solution. Now, obviously, this recipe can fail. For example, what if you simply cannot find a separation ansatz? I mean, that basically relies on that the different variables are also not mixed, that they're not terms where they're mixed dt, dx derivatives, for example, right? Well, you could still try to go to a different coordinate system. Maybe actually it separates out in radial or in polar coordinates or something like that. So this is something to try out. Another case where, of course, it could fail, maybe it's not a Hermitian operator. Could also be. It turns actually out that there is a more general theory that you can actually find a more general scalar product that with which you can actually get an Hermitian operator. This is so-called Sturm-Liouville theory. So if you ever need that, then at least you know a name where you can look it up. Yeah, and if all of this fails, well, simply resort to a numerical solution with the computer.